So today I'm going to be saying a little bit more about the use of pulsar timing as a method to detect gravitational waves. Yesterday I was covering just how pulsar timing is done and how the timing model has to be used to barycenter the data, and so and that's going to come up again actually because it impacts the gravitational wave analysis. So this is the outline of what I want to cover today. I'm going to start with a little on the sources in the nanohertz band. I haven't actually compared notes with what Alberto Cesana is going to talk about later today, but I know that he will be talking about supermassive black hole binaries, both in LISA and for pulsar timing. So I'm going to be very brief on the source part because Alberto is going to cover more of that. Then I'm going to get into pulsar timing data analysis. It's somewhat different than what you've heard about for LIGO. I'll say something about stochastic signals, then the possibility of detecting individual supermassive black hole binaries, including bursts from the memory effect, and finish with a little bit on using pulsar timing as a way to test alternative theories of gravity. So that's the menu for today. So in terms of the sources, there are some exotic possibilities and then the more astrophysically expected. So under the exotic possibilities, you've got things like cosmic strings, phase transitions in the early universe may be producing stochastic signals in the nanohertz band. The sources that we are most confident about seeing are the signals from pairs of supermassive black holes, and we know these are just images of actual, not the same galaxy obviously, but galaxies in various stages of merger. So galaxies merge through the history of the universe. Essentially all large galaxies seem to host supermassive black holes, so once they get together, dynamical friction, as Alberto will tell you, can bring them together, and you can maybe harden them up to eventually form a binary system. And when we actually catch them in the pulsar timing band, unlike LIGO, which is catching the final merger and ring down, we're actually seeing the early in-spiral. They're just, sedately orbiting around each other thousands of years before merger. So we're seeing them a long time before merger, quite simple signals. Another possibility, though, is if they do merge, there is this offset. The gravitational field does not go back to the same value. You get a permanent shift in the gravitational field, and that leads to an observable effect in pulsar timing. It's also observable in LIGO, but LIGO has and LISA, but because it's the overall effect is a DC offset, but it has to ramp up. And it's that ramping up that you can measure in LIGO and LISA, because you can't measure things at zero frequency in LIGO and LISA. But the way pulsar timing works, you actually do see that that offset, because it just leads to a linearly increased signal. So I'll say a little bit about these later. In terms of predictions, here's some predictions from Joe Simon and Sarah Birks-Ballard, where they're estimating what the sensitivity of pulsar timing rays might be going into the future, and in population synthesis models where the individual black hole signals might be. So we've got this whole collection of black hole signals which combine together to form a background, but in addition there should be some individual sources that stand out above the background that we can pick up as individual bright sources to detect. And so the idea is we've got, over the entire history of the universe, we've got this sequence of mergers happening here with nicely indicated black holes in the middle, red as they merge, and then mergers following mergers, building up this signal. And again, this is something that Alberto is going to tell you a lot more about. Now this isn't a scary looking equation, but I'll just break it down into its components. So what we traditionally do is approximate the signal from this ensemble of supermassive black holes as an isotropic stochastic background. It's actually not going to be isotropic and it's not going to be truly stochastic, but let's just pretend that it is for a moment. Then we characterize, as Joe would have told you, for stochastic background in terms of a power spectral density, which can be written in terms of the characteristic strain. And then you've got these factors of f cubed here. But this characteristic strain, you're basically adding up. This is the sum over redshift, mass ratio, and these various terms. This is the black hole merger rate. So n is the number of sources per redshift, total mass ratio as a function, over time. This term here is if the binaries are in eccentric orbits, you have to sum over all the harmonics of the signal. So this is adding up, because we're doing it at a particular frequency, but you got contributions from all these different harmonics. This term here is the orbital decay rate from the emission of gravitational waves or other factors that might be driving the binaries together. And here's the sort of instantaneous gravitational wave strain at that frequency. So that expression looks kind of messy. It was first derived by Finney. This version of the expression I stole from one of Alberto's papers. Let's take a simpler case where let's ignore eccentricity for a moment and just consider circular gravitationally wave-driven mergers, in which case we can figure out what the various factors are. As you probably recall from earlier lectures, the time rate of change of the frequency scales as the frequency to the 11/3 power. So a little bit of simple math then tells you that this factor of dt d log f goes like f to the minus 8/3. The instantaneous gravitational wave signal, of course, scales as f to the 2/3. So you put in f to the minus 8/3, f to the 2/3 in here, and then take the square root, and that gets you f to the minus 2/3. So the prediction is that if you have circular gravitationally wave-driven inspirals, then you end up with a characteristic strain that goes as frequency to the minus 2/3 power. So in the simplest models that we try and constrain with pulsar timing, we quote constraints on this amplitude here. It is the amplitude of the characteristic strain at a reference frequency of 1 year, right? Since it's a spectrum, you've got to pick a point to reference it to. Ironically enough, pulsar timing has 0 sensitivity at frequencies of 1 over a year. Why is that? Can anyone guess? Why cannot we measure any gravitational waves at a period of 1 over a year? Right. In what way would you think? From what I told you guys yesterday. What do we have to do in pulsar timing to when the signals come in? Remember, we have to reference it to the solar system barycenter, right? So what's happening is that the timing model, we have terms in the timing model that are at the period of the Earth's orbit, because a lot of those effects were at. So we actually completely fit out any gravitational wave signal gets absorbed by the timing model. So we cannot detect things at a frequency of 1 over a year because it's completely eaten by the timing model. So it's kind of ironic that that's the frequency that we reference the amplitude at. But okay, so that simple derivation that I gave was for circular binaries that are just gravitationally wave driven. So they're it's just the emission of gravitational waves that's causing the orbit to shrink. There are factors that can affect that prediction at these binaries had to get into the sub-parsec gravitationally wave-driven regime somehow, and there's various mechanisms for doing that. So after dynamical friction has brought the binaries within a parsec or so, you then have to harden the binary further down to hundredths of a parsec before the gravitational wave emission takes over. So some of the possibilities, you might have gas, and you might have various stars where the actual binary scatters stars out. And also I was neglecting eccentricity, and some of these processes can actually drive up the eccentricity of the binary. All of those effects tend to diminish the signal at low frequencies. So instead of going as this f to the minus 2/3 power law, you know that can't continue forever because it would be infinite. So these effects are going to cause the spectrum to roll over at some point, and exactly where it rolls over is going to depend on the details of what's happening in the in terms of stellar hardening and things like that, and the eccentricity distribution. So one of the things we will learn once we start detecting signals in pulsar timing is by measuring not just the amplitude at 1 over a year, but the shape of the spectrum will inform us about the processes that actually bring supermassive black hole binaries together, right? So there's going to be additional astrophysical information from measuring this spectrum eventually. So these are the various environmental effects that can actually cause. You might have this pinkish band here is if some of those binaries just never harden. They just get to a certain point and stall, and so you might potentially not have some of the binaries actually getting together and merge, which cause the signal to be diminished somewhat. And also there's uncertainties on the amplitude here because we have a fairly decent idea about what the what the galaxy merger rate is. That's pretty well measured, but there are uncertainties in the relationship between the masses of black holes and the masses of their galaxies, and that adds a factor of a few uncertainty in what this amplitude might be. Again, this is something that Alberto will cover. I hope. I keep on saying what he's going to cover, but you know. But it's a similar. Yeah, just they're lower mass, right? Alberto also does the PTA stuff as well, so I was thinking he might cover some of that. But it's a lot of similar aspects to it, except I think in LISA, gas dynamics is probably more important than it is for pulsar timing. Okay, so these are the sort of things we're going to learn about. These uncertainties in the population synthesis models that we have right now in predicting what the signal will be, if you turn that around, once we make a detection, it will be informing us about all of these processes, right? So that's what we're going to be learning astrophysically. Now, it turns out that this approximation that the background is isotropic and stochastic is not really true. When you actually, here's a simulation from a population of black holes showing the power on the sky, and this goes from 0 to 100 on some scale here. This is a statistically isotropic stochastic signal with the same power spectrum, and this only goes from 0 to 2. And so you've got these hot spots because of the individual binaries. As you saw back from that earlier simulation, there's sort of individual bright sources that sort of stick up. And in fact, when you look at it, over 50% of the power comes from less than 100 black holes. So you're dominated. In fact, you know, just 10 or so black holes account for a good chunk of the power. So it's going to be not really stochastic, and we should, it's somewhere between being more like a stochastic background or just individual sources. Oh, to amplitude, but so you can actually, as I'll talk about a little later, you can actually try and detect individual signals, but the technique that's currently mostly being used, we actually use it, we do that search as well, but the main technique is still a cross-correlation technique between taking the signal in one pulsar and cross-correlating it with a signal in another pulsar, and I'll explain that a little bit more. So the majority of the results that have been produced over the years have been treating it like a stochastic background, where the only way that you could get at it would be to do cross-correlation. If you know that it's not really a stochastic background, but it's made up of individual discrete sources, there are other ways you can analyze the data that can be more effective at finding the signal. In fact, Joe and I wrote a paper a few years back where we did essentially a toy model, which was a collection of sinusoids, and we compared trying to detect all the sinusoids sort of individually versus trying to detect them, just treating them as a stochastic background. And we also had a model that was a bit of both. It said, okay, some component won't be individually resolvable. We'll treat that as stochastic, but then we'll have a few brighter ones that stick up, and we showed that combined model, which is partly individual bright sources plus stochastic, actually always got the detection first. So we're not doing that right now in pulsar timing, but we're about to start doing that. That's a project that's ongoing in NANOGrav right now, is to do this combined analysis where it's both at once. Yes, yeah, that's why, since I work in LISA and pulsar timing, I don't actually really have to change the techniques too much because they're very similar problems. Yeah, you saw right through it. Okay. So you heard a lot about gravitational wave detection for ground-based detectors. Martin covered it for space-based detectors, but I'm going to now go through pulsars as gravitational wave detectors because they're somewhat different in their mode of operation. Now, all of these, this is taken from a Living Review article that Joe and I wrote, and I think it's a good resource on many different aspects of gravitational wave astronomy. One of the things there, we were trying to present a unified viewpoint of gravitational wave astronomy where, whether it's pulsar timing, maybe spacecraft Doppler tracking, which really isn't used very much these days, laser interferometers, all of them are essentially time of flight detectors. In the case of pulsar timing, we've just got a signal coming from the pulsar going to the Earth, and the gravitational waves are creating some kind of a fluctuation in that arrival time. With an interferometer, you know, you have to, here's the world, this is a space-time diagram, so there you're sending the photons down two paths, and you have these time delays. The thing you measure in each case is somewhat different. In the case of pulsar timing, you directly measure this time delay. In the case of spacecraft Doppler tracking, you actually measure the change in the frequency, so the Doppler shift. In the case of a laser interferometer, you're measuring the phase shift. And the problem there is the phase shift depends on the laser frequency, and that's why if you have fluctuations in laser frequency, you get a problem, right? But in pulsar timing, you're just directly measuring this time delay. So I'm going to go through a calculation of this time delay because it's different for when you have to take into account that the gravitational wavelengths can actually be, in the case of laser interferometers, the wavelength of the gravitational waves is typically much larger than the size of the detector. That's not true for pulsar timing. So in the case of, and this again is from our review article, here's the sort of scale in kilometers of the detector. Here is the sort of, now this F star is the frequency at which the gravitational wavelength would be equal to the arm length of the detector. So that's when you have to start taking the sort of finite arm length effects into account. So for ground-based detectors, that's around 10 to the 5 hertz, which is sort of outside of where we usually are analyzing things for ground-based detectors. For space-based interferometers, it's around a tenth of a hertz, and so LISA, for example, is sort of spans the two. It's partly in the low frequency response regime, but all those wiggly things that you were seeing in Martin's plots came from these finite arm length effects, right? So LISA actually is partway between, and pulsar timing, though, is at the other extreme, where this frequency at which you'd have to worry about finite arm length effects is actually much smaller than the frequencies you're trying to measure. So it's this situation. You've got, you know, thousands of gravitational wavelengths fitting between you and the pulsar. So it's a completely different regime. The calculation's the same for all of them, but people usually only show the short, they take the particular limit for LIGO, so I'll just go through the derivation in general. This is based on the original derivation was by Estabrook and Wahlquist, and I'm just sort of repeating it here. So if you write down the metric for a gravitational wave propagating in the z direction, gravitational waves always go in the z direction. I think you've probably noticed that by now. Then if you make a change of variables to t minus z and t plus z, then you get the metric like this. And you notice that this metric does not depend on z, so that's going to be a killing vector. So the nice thing is, when you've got a lot of symmetry, if I want to actually solve for geodesics in this space-time, I have 3 killing vectors, because the metric doesn't explicitly depend on x, y, or v. And then you also have the normalization condition for null geodesics. So that gives you 4 conditions, so the trajectory is fully specified. So you don't actually have to solve the differential equations, because you've got 4 constants of the motion, so it's just an algebraic problem rather than a having to solve a differential equation. That no one ever really wants to do that. So the basic idea is the following. Suppose at some reference time 0 here, at time 0 and location 0, you emit a photon and it goes over some affine parameter, lambda 1 to lambda 2, so delta lambda is just lambda 2 minus lambda 1, and arrives at x, y, z, and then the time, of course, this is in the unperturbed space-time, is just L, and these are the 4 velocity components, but the downstairs ones, which are the conserved quantities, for the in the unperturbed case, and that just gives you that t has to equal L, right? So this isn't very. But then when you actually now include h, you have to slightly perturb. If you want to arrive at this location over here, you have to sort of perturb where you fire your photon. You're going to end up at a perturbed location here, and it's a simple calculation to go through that, applying that same conserved quantities, but now in the perturbed space-time, you have to perturb the direction that you fire the photon, and you end up with this as the time delay here. Capital H is the antiderivative of the gravitational wave signal, right? Integrated with respect to u. And so that is the general expression for a time delay. And here I was doing it just for a gravitational wave going in the z direction. And I've now defined the plus being hxx minus hyy, and this is the cross. You can write this in a coordinate independent form, where I've got, if A is the vector pointing along the unperturbed photon path, then that expression here is just this is the general coordinate independent version of that. You can easily calculate that this gives this for that particular case I gave you. And so this is the general expression for a one-path perturbation due to gravitational waves, the time delay. And this is valid for, there's no assumption made about the gravitational wavelength being small or large compared to the length of the arms of the detector. All right, so just to give a concrete example, if I just took a sinusoid gravitational wave that's just a plus polarization, just plug that into that general formula, which I just have repeated here, then this is what you get. So just plugging this in here, the first term you get, this is the gravitation, the A hat was the direction along the arm. And so this is just this tensor product contracted with the polarization tensor. So this is the long wavelength one arm antenna pattern. So this is actually what gives the usual antenna patterns you see for LIGO, but there you've got one going up and one coming back, right? You've got this sync function here, which is actually encoding the finite arm length corrections, and here it's just actually the phase of the wave evaluated at the midpoint of the arm. So this is the general expression for if the response to a sinusoid, and this correction here is what is the finite arm length correction to the antenna pattern, right? So if I did this for pulsar timing, where I've got a pulsar a distance L away in the A hat direction, I've got a black hole a distance D away in the N hat direction, you've got the gravitational waves perturbing the path here, mu is the angle between the black hole and the pulsar. That's the general expression for the response here. Whoops, that psi should be that one, it's just the polarization angle. This is what the antenna pattern looks like for, say, the plus polarization, and it has this wild pattern from the sinc function. This was for a case where the frequency times the distance equals 10, right? So the usual quadrupole type pattern has become, has become like an onion, and this is the gravitational wave propagation direction. The colors indicate the intensity. So you notice something right away is that in pulsar timing, you are most sensitive to gravitational waves. A pulsar that's close to the gravitational wave source on the sky responds most strongly, right? So if a pulsar is here, it responds much more, it has a much greater response to a signal coming from a black hole at this location in the sky than a pulsar over here. So that we'll see that effect happening. So that's what the antenna pattern looks like. If I ramp up, this actual value of f times L equals 10 is actually on the very small side for pulsar timing. The typical numbers for frequency times path length is more like thousands to tens of thousands. So this becomes extremely, to the point that you can't see the nice little leaves anymore. Yes. And the gravitational waves coming down like that, that's right. And see, you don't really respond very much if your pulsar happens to be, in the opposite direction to the source, you get really no response, right? You don't see, that's right. Except, like I was saying, these leaves are actually extremely closely spaced because this f times L is a lot larger than 10 typically. So, yes? It's because it's a sinc function, right? You're seeing sinc is sine x on x, so you're just seeing the physically. Well, it's basically got to be. It's a good question. It's like the cancelling. It's like it's exactly. See what? Here's the way to think about it. Imagine you've got. I kind of think of it more in the LISA context for these things, but let's do it for LISA because it's the same sort of idea. So you've got your photon propagating from one spacecraft to another, or if it's pulsar timing, it's the. And imagine that the gravitational wave, if the period of the gravitational wave is equal to the light travel time of your photon, you find the detector back where you started, and so you get zero response, right? Now that's going to depend on, it's actually the projected path length that matters here, right? Depending on where you see it on the sky. So there's different locations on the sky. Well, it's the arm length vector dotted into the sky location is actually what sets that time scale. And so for different sky locations, you just get no response. So that's with LISA, for a particular sky location, you can get zero response. But then what Martin was showing was averaged over all the sky, and so instead of getting a complete zero, you get some wiggly pattern. Here, there's just going to be pulsars at particular locations on the sky where you get, you just catch it an exact, oscillation of parts. It's just doing nothing. Right, it's retarded, and it's canceling out. Yeah, right. So yeah, so that's what's going on here. So that's what's going on here. Well, this goes into figuring out where the gravitational waves are coming from. This information is part of what then helps us, because we've got the response from lots of different pulsars, and so that helps with our angular resolution, right, the response. Okay, so let's get into that a little bit in the pulsar data analysis now. Again, if you have Gaussian noise, which isn't always a great approximation, but this expression for the likelihood, which is your noise model, it's the same for every, this is the same likelihood for LIGO, it's the same one for LISA, same for pulsar timing. This is it. This is the likelihood for gravitational wave data analysis. And so, again, Joe and I have been trying to unify all of gravitational wave analysis, right? The response, formalism, the likelihoods, just it's all the same. And so if you want to work in pulsar timing and on LISA and on LIGO, it's better to think of it as all being the same, because that way you don't have to like learn something new every time. Okay, so let's go through this. Here D is the data, which in the case of pulsar timing is the pulse arrival times for all the pulsars. Lambda's the model parameters. Now that includes for pulsar timing the timing model, and I talked about all those parameters. So each pulsar has a collection of parameters that you need for the timing model. There's a bunch of parameters associated with the various noise levels, and then there's also parameters that have to do with the gravitational wave signal. So you've got this big parameter set. R are the residuals, so that's the data minus the gravitational wave signal. In the case of pulsar timing, it's a little bit trickier because the data, first of all, you have to subtract the timing model. So you've got the raw data minus the timing model, then minus the gravitational wave signal to get your residual. So it's a little different from, in the case of LIGO, we don't have to, subtract this part off, nor for LISA. C is the noise correlation matrix, and M is just the total size of the data set, and so that's the size of this matrix. It's an M by M matrix, and here we're summing over from I equals 1 to the number of pulsars. So this expression's general. It works just fine for any gravitational wave analysis if the noise is fairly Gaussian. Okay, so let's break it down a little further here. In the case of pulsar timing, this inner product here, so that's the inverse of the noise correlation matrix. Here are the residuals. Now, the big I and big J label which pulsar, okay? So you've got a network. In the case of LIGO, I and J would be, the Hanford detector, the Livingston detector, and then the Virgo detector. So this is which detector. A is in the case of pulsar timing, it's the arrival time. In the case of LIGO, it would just be the timestamp for each sample. And so this matrix depends on I and A and J and B. So you've got this big matrix here. Now, if the noise is uncorrelated between the pulsars, then this matrix has a delta function, ij, so that it's uncorrelated between pulsars I and J. And the same we hope for LIGO. It's not true for LISA because it's sort of all one instrument, so you don't get orthogonality there. But you've got hopefully uncorrelated noise between the pulsars, and then you've got the noise spectrum for the ith pulsar, and this is a function of the time of arrivals A and B. Now, because there's going to be red noise, samples taken at different times are going to be correlated. That's what red noise does, right? The timing model is definitely correlated across them, but it's not part of the noise model, right? It will be in a minute, because we kind of factor it in, but primarily it's not. It does become effectively like a noise term, as you'll see in a second here. All right, now pulsar timing data analysis is much nastier than anything else I've ever encountered in gravitational waves because it's unevenly sampled. The noise is non-stationary. The error bars on each, as you might have seen from some of my plots yesterday, the estimated error bars on each time of arrival are different, right? So it's a that's called, there's a term for it, it's called heterostochastic. I can't even say it. There's a word. Anyone? Sorry? Yes. Can you say that again? 5 times? Yes. Okay. Which is just horrible. Because it's unevenly sampled and you can't easily go to the Fourier domain, so the analysis is conducted directly in the time domain, which means that this matrix you have to invert. Just directly invert this matrix. If you recall, for stationary noise, so it only depends on the time lag between the samples and not on when the samples are taken, right? So if the noise is stationary, then this noise correlation matrix is diagonal in the Fourier domain. That's why we go to the Fourier domain for LIGO Virgo data analysis. But but here we can't easily go to the Fourier domain. The noise isn't stationary anyway, so it wouldn't buy you much. So you just got to deal with these big matrices, and these matrices are now getting larger and larger as we collect more and more time of arrivals, and we have more and more pulsars. We're up to sort of 50-odd pulsars now, many of them having thousands of time of arrivals. So you get this huge, great matrix that you have to invert. And you have to invert this at every step of the likelihood because you're updating your noise model. So you've got this massive matrix to invert, and if we had to do it just naively, like if you just took that giant matrix, even with the best matrix inversion algorithms, it would take you, minutes to evaluate each likelihood evaluation, and which would make the analysis essentially impossible because we need to do lots of likelihood evaluations, especially if we're using Bayesian techniques. So some clever tricks have been invented. I think actually, to be honest, more like you find it in other fields. People have not rediscovered actually. You read papers from people working in other fields and adopt clever techniques. Anyway, so this was done by Rutger van Hasten, and Michele Vallisneri came up with implemented some clever tricks to dramatically speed up the inversion of these matrices, right? So you can read about it in a paper they wrote. Okay, so for the timing model, which I wrote as capital tau here, sorry, not capital, boldface tau, you have the reference timing model. So the way it works, when you go out and analyze the data from an individual pulsar, you don't worry about gravitational waves at first. You just solve and try and get the timing residuals as clean as possible just for that one pulsar. But in doing so, you potentially have eaten some of the gravitational wave signal. So we just take this as the reference solution. So this is the solution where we haven't yet accounted for the possibility there's gravitational waves in the data. So it's our reference solution, but then we allow for a perturbation because that solution might have been thrown off a bit because there were gravitational waves affecting the time of arrivals, right? So this may already have eaten up some of our gravitational waves. So what we say is, okay, we better not just use that solution because then we've probably killed the gravitational wave signal, or at least some portion of it. So let's take that as a reference, but let's perturb it by a little bit. The gravitational wave shouldn't really change the timing model much because gravitational wave signal should be pretty weak, right? So it's essentially a Taylor expansion, and you can write that as a design matrix, which is essentially a bunch of coefficients essentially from a Taylor expansion times the timing model parameters. So it's just the first term in a Taylor expansion, right? So these are basically the the derivatives. So if the solution depends on a set of parameters, this is just the set of partial derivatives of the model with respect to those parameters, and then these are the parameters. So it's just this is a Taylor series to leading order, right? So what we do is we can calculate this design matrix. These then are the parameters that are unknown. It's our little perturbation to the timing model. And what we can do is we can replace the noise correlation matrix by this matrix here, explained in this paper. And as I was saying to Martin a moment ago, that's where we essentially now have put some of the timing stuff now ends up into our noise correlation matrix. So let's see what happens if we want to try and detect a stochastic signal. So this is the likelihood again. I've been talking about that for a little while now. In the case of a stochastic signal, you have a prior on what the signals look like, right? So it's a prior on the gravitational wave amplitudes, and it's that they follow a Gaussian distribution, multivariate Gaussian, with some power spectrum. So we aren't necessarily interested, if it's a stochastic signal, we're not necessarily interested in the individual values of the gravitational field. We're interested in its power spectrum. So in Bayesian analysis, anytime you aren't interested in something, you marginalize over it. So what you do is you integrate over the gravitational wave signal, and that has the effect of taking the noise correlation matrix and replacing it by the noise correlation matrix plus another matrix, which now has the gravitational wave power spectrum in it. To read the details is in a paper that Joe and I wrote in 2013. And here, the correlation, remember in the case of the noise, we were assuming that was independent between pulsars, that was a delta function. Here it's not a delta function. There's a correlation factor here, which is the Hellingsdowns correlation. So just saying that again, this new matrix has the noise term, which is uncorrelated between pulsars, and then the correlated gravitational wave signal. So we've integrated out the individual samples, gravitational wave samples H, and now all we're interested in is just the spectrum of the signal. But notice it came from exactly the same likelihood. There's no talk of cross-correlation here. I mean, it's literally subtracting off a template in the same way we do all gravitational wave analysis, but in this case, we've marginalized out over things we don't care about, which are the individual, we don't care what the signal is, the stochastic signal is at each second. We only care about its spectrum. So here it's, so there's no talk about cross-correlation, but it naturally brings in, this emerges naturally in the analysis, as you can see in that paper that Joe and I wrote, that it naturally recovers the Hellingsdowns correlations curve, but just doing it as a template-based analysis, which we thought was pretty cool at the time. But no one seems to have really read the paper, so we're the only ones that that think it's cool. All right. So here is this characteristic shape of the Hellingsdown correlation curve. In a lot of treatments, you'll see this normalized to unity. Here, I have it, as a third. This is actually what you get if you just directly do the calculation. Then people just renormalize it to 1. But I like to leave it in its original form. This is actually what you find in Ron Helling's and George Downs' original paper. Is like that. Okay. So that's the smoking gun. That's what we're looking for. So here are some results from the most recent NANOGrav analysis. So NANOGrav now, our most recent data release was the 11-year data set. We have the 12.5-year data set coming out soon. I don't know quite why we started doing half-year data sets, but anyway. But from the 11-year data set, here is our inferred values for what the correlation is as a function of the separation between the pulsars. Right, so these are our measured correlations with the error bars on them. And here is the Hellingsdowns curve. If it was, that's what we're hoping to measure. And you can see the current status of things is our uncertainties in our measurement of the correlation function are a lot larger, so we're not really we're not seeing the correlation yet. But it's even when we do start to see it, these error bars will still look large compared to this, because it's the combination across all the angles that we end up putting together. But still, right now there is no evidence for the correlation pattern, we're not seeing any gravitational waves in the data right now. Well, what we've done is we've binned things, right? So we have, you know, I forget exactly how many pulsars we had in the 11-year data set, but 40-ish, yeah. That's right. Well, you got to remember, you've got all the you get n times n minus 1 on 2 pairs, right? So you get a lot of pairs, and actually what I probably should have shown, I think we have it in the paper, we have a plot of what our coverage in angle is we have all the pulsar pair angles plotted, like how do we actually sample, and it actually of course follows a cosine distribution, so you have very few samples here, and you have much more in between here. So if I showed this as cosine of the angle, then it's a uniform distribution, but I'm showing it as a function of angle, so we've got, you know, a certain number of pulsars at each and then we've binned up collections of them to produce the correlations at, you know, how many we got? 1, 2, 3. It looks like we've got like 20-ish. I don't know. So we've binned it up. Maybe they're 10-degree bins or something like that. That's right. Right. Yeah. But this is just sort of we don't actually use this in the analysis. This is one of those plots you like to show just to give people a feel for where we're at on how close we are to being able to, I mean, we quote things like Bayes factors between seeing a correlated signal and not seeing, you know, and those Bayes factors are like, there's nothing there. But rather than just quoting a single number, you can visually see right now we do not have sufficient accuracy in our measurements to really be inferring the correlation pattern. But this is the smoking gun, if you remember. The fact that the gravitational wave signal will be correlated between all the pulsars, whereas the noise won't be, that this is what we need to see to claim a detection, right? Just finding a red signal with the appropriate slope is not going to be convincing. Yes? Yeah, it's quite enough. Now as I realize, I should have put in the plot that shows the distribution of the pulsar pair angles that we actually have. We're lacking pulsars with these kind of angular separations, and we have a whole clustering of them around here. So some parts of this curve are really well sampled. And the other thing is, not all the pulsars are equal, unfortunately. So when we say we have 45-ish pulsars, well, some of them we've only been timing for a few years, so they don't really contribute as much. Some of them just aren't as good at timers as others, so we're kind of dominated, actually, by a much smaller subset of pulsars. There's really only like 4 or 5 that kind of dominate most of the likelihood. So when you take 5, the number of pairs you get out of 5 isn't very large, so we're still sort of, we don't really have as big an array. The effective size of our array is not that large so far. It's because I'm going to show you the distribution of our pulsars. It's because of where this is NANOGrav, not the International Pulsar Timing Array. So we have our radio dishes are in the northern hemisphere, and one of them can't move. So it can only see a band of just whatever goes above Arecibo is what we can see, right? The other one's steerable, so we can see more of the sky. But we don't have any of the southern hemisphere pulsars, for example. And that's why the big advantage for us in working with the Parkes Pulsar Timing Array is we get the southern hemisphere pulsars then, and that gives us much better sky coverage. So, all right, another one of the results that we have in the 11-year paper is our bounds on the characteristic strain, and these are bounds that we derive at each individual frequency. So the black line is what we derive we did it frequency bin by frequency bin, and these are the upper limits we have at each frequency. And you see this spike really goes to infinity here. This is the at 1 year we don't have any sensitivity. But this is sort of bins, so it gets smoothed over. These colored bands are predictions from the literature. And so there's a prediction from Sean McWilliams and collaborators that's up here. And I would say at this point Sean's prediction is pretty well ruled out. It was a very optimistic scenario. More moderate scenarios are starting to get very close to being either discovered or ruled out. And then there's a more pessimistic model. This one happens to be from Alberto and some of his collaborators, and it's down here. So, some models are already getting ruled out. Others are right on the cusp of either being detected or ruled out, and then we're going to have to wait a little longer to get down to some of the more pessimistic models. That is the timing model. So we can absorb out any gravitational wave just by in the timing model by when we're solving for the location of the Earth relative to the center of the solar system, it just gets completely swallowed in that, because that's a big effect, right? And this turn up that happens here is because we actually have to fit a quadratic to the individual pulsar. The pulsar frequencies are evolving. If you remember in the timing model, there was a term that there was the frequency derivative, and second derivative. And in fitting that quadratic, that actually takes out, fitting a quadratic to data, removing a quadratic from data is a form of high-pass filter, right? Not a very good high-pass filter, but it's a high-pass filter, and that means that we are insensitive. We lose sensitivity to the low-frequency gravitational waves because we had to fit out. So that's the timing model again. So the timing model causes this. Otherwise, it would have just continued as this f to the 3/2 power law. And the timing model leads to an insensitivity at 1 over a year, and actually also at 1 over 6 months. With that spike we don't really see here. All right, so that's the current status for stochastic signals. Oh, important point that we ran into a problem. So when we first started analyzing the 11-year data set, at first we had a signal. And we even had some indication of correlation across the sky. And so we were sort of getting a bit excited that maybe we're finally seeing something. But, you don't go rushing out and publishing something like that. You drill down deeper and make sure that it isn't some kind of a noise issue. And as I said, part of the timing model is that you have to barycenter the data. And to do that, there are these ephemeris models, and there's a group in France that makes these models. There's a group at JPL that makes them, and I think there's one other group in the world that makes these models. And it's based off, collection of data from all the different missions that go out through the solar system. And these are the code names of some of the ephemeris models that have been put out over the last few years by the JPL group. And you can plug in different ones. This tempo timing package, you can sort of say which of the models you'd want to load in. And I guess someone did the analysis with one model and did it with another and found we get very different results. So this is the log of that amplitude referenced to 1 over a year of the characteristic strain. And here's the posterior distribution function shown on a log scale. And you see that the faint dotted lines are what you get if you analyze the data using just the different ephemeris models. And you see that you get very different answers depending on, and you're getting this peak here, and that was indicating a detection. Because a detection, when you get a detection, there would be no weight at low. So in fact, the value here, you can use the Savage-Dickey density ratio to estimate essentially what the Bayes factor is for there being a signal. So if this goes to 0, your Bayes factor goes to infinity. So the fact that, for example, this particular DE430 was giving a very significant indication that we were getting some kind of a signal, whereas say D435, there was really nothing there. So we knew something was wrong because, you know, there's got to be a right answer for where things are in the solar system, right? So you can't just pick your favorite one that gives you a detection. Okay, so, and also it's not okay that the result depends on this. So what had to be done, there's a paper that's not out yet. It's work done by a group of people, including Michaela Vallisneri and Steve Taylor and a few others. They actually added to the timing model parameters, they had to include things like the mass of some of the large planets and orbital parameters like changing the eccentricity of, say, Jupiter's orbit, right? And then solve for that. Because what it was telling us is these models for where we are in the solar system aren't accurate enough. So we now have to solve for the masses and orbits of the outer planets ourselves, because the JPL, you know, it's fine if you just want to fly a spacecraft to Mars. There's stuff, because you don't have to get, once you get close, right, you can sort of like, you know, it's a pretty big target. But we need to know where the center of the solar system is to better than 100 meters, and the ephemeris models don't give us that. So now we're now, the funny thing is, the people at JPL, they think that they know what the mass of like Jupiter and Saturn is, but we're changing those values, and they're not really happy about that. But without it, this doesn't work. So anyway, so we're now actually solving for the masses and orbits of planets as part of our modeling. Yes, Joe.
So is it like the timing model description that you had before, where there's a reference ephemeris model, and then you add?
That's right. Exactly. That's right. And you know, that's going to be described in this paper coming out soon, and I think we're probably going to improve on that model as we go forward, but we've got one that works for now. And so what these dark lines are is where you start with the reference model being any one of these ephemeris models. Then we have the perturbation to the ephemeris model that we've now included, marginalizing over those new parameters, and you see now we get the same result regardless of which starting one, and that's what you want to see. Your answer should not depend on which model for the solar system you use, and we've been able to connect all of these now, so we get the same result regardless of our starting point. So that's our latest bound on what this amplitude is. It turns out that our 9-year analysis was wrong because we hadn't realized that this was happening, and so people were wondering, why has our upper limit got worse even though we added in more data? Well, it didn't get worse. It turns out that our old upper limit was wrong. When you analyze it, accounting for this problem with the ephemeris model, you find that indeed the true upper limit we had from the 9-year data is not as good as the one we now get from the 11-year data. So, but it looks like we went backwards when you actually look at our values published. Yes, Cliff. Yes. I don't believe so. It turns out that there's only, I think it's just Jupiter is the only, when you look at these parameters that have been introduced, it's the orbit of Jupiter is the only thing that we really need to play with to get this to connect. So, you know, I think as we go forward, we're going to, as our sensitivity improves, we're going to, you know, start to be more and more sensitive to. In fact, one of the so on the space station right now, there's the NICE mission, which is principal goal is to try and constrain the radius of neutron stars so we can get constraints on the nuclear equation of state. But a second project that they're doing is actually using pulsars as a celestial reference system as a way to, you know, fly spacecraft around. And so the idea is eventually that using pulsars as our reference is going to be the best model for the solar system. And so, you know, going forward, potentially we'll get, you know, more and more effects. And actually one of the things as the time scale goes up, we think that it might potentially, you know, people have been wondering if we might detect like Planet 9 or something using pulsar timing. So the effects of that, you know, there's supposed to be this other planet out there on a very long period orbit, and we might eventually start to detect the influence of that other planet, which would be cool. Okay. So where are we with stochastic signals? How long before we can expect a detection? In an effort to answer this, there was a recent paper led by Steve Taylor. There was earlier work that included Joe, Javier Siemens, Justin Ellis, Rick Chenet, and the scaling for how the signal-to-noise scales depends on whether you're in the weak signal regime, where you're sort of dominated by your other noise sources, or where you get to the strong signal regime, where the dominant noise source is actually the gravitational wave signals, the uncorrelated bit from the pulsars, which I didn't really talk too much about, and I probably should have. And so the scaling starts off nice and steep as time to the 13/3. It goes over to time to the half, and it scales with the number of pulsars. So you want lots of pulsars, and in fact, these scalings with time hide the fact that the number of pulsars is increasing with time because we keep on discovering new ones at a rate of about 4 a year. So we keep on adding new pulsars to the array. So this n number of pulsars is a function of time as well. And if you put all of that together, that's what into this analysis, you get these predictions, and this is for the Parkes pulsar timing array. This is the expected detection probability. Now the Parkes group has always had the best upper limits, but you can see that even on their own, even if we go out 20 years from now, they'll be at most at a 10%-ish probability of making a detection. It's just they don't have very many pulsars. You need lots of pulsars. If we, let's focus on this. This is the IPTA when we combine the data from all of the pulsar timing arrays. The blue is if for every galaxy merger, the black holes eventually get together and start creating gravitational waves. The red is if only 10% actually get together to start that they don't solve that last parsec problem, they never get into the gravitational wave regime, only 10% of them do. So this is a more pessimistic scenario where not so many of them actually emit, so that basically says that you take the galaxy merger rate and you have to downweight it by a factor of 10 to then get the black hole rate. The dashed is whether there's these environmental effects kick in, say at 3 nanohertz. You see that the knee doesn't really affect our ability to detect things very much. And this is starting from today, where we're at with the data today. And so in the more optimistic scenario, we should make a detection, probability of detection, gets above 50% within 5 years. In the more pessimistic scenario, we're going to have to wait a bit longer. But in order, somewhere between the next 5 to 10 years, pulsar timing should make a detection. Okay? So now that's assuming that we don't come up against some other noise source. I mean, each time you get a little bit more sensitive, we came up across this problem with the solar system ephemeris. Who knows what new problem lurks in the data as we become more and more sensitive. So these projections are under the assumption that no nasty surprises come up. But I'm fairly hopeful that we'll get there pretty soon. Yes. For the right, well, we have someone far more expert in the room to talk about that. The possible, actually, Alberto wrote a paper recently. So imagine you've got 2 galaxies merge, and the black holes, dynamical friction, they sink down to the center of the merged galaxy, but they get to about a parsec or so apart, maybe a bit closer, but then they still haven't got into the sub-parsec regime where gravitational wave evolution is going to drive them. And they just sit there, right? In that case. But then along comes another galaxy, merges with that merged galaxy, and we know this happens as a sequence of mergers. Now you've got another black hole comes in, sinks down. Now you've got 3 black holes, and then they start dancing, and there's all sorts of crazy stuff that happens, and that can actually lead to hardening of a pair of them. And so the possibility of sort of getting a 0% merger seems, not really viable. It seems like these kind of 3-body effects would eventually get you some mergers. So I think we sort of have a bottom line now for what the merger rate's going to be, and I don't know whether 10% is where it would be, like of what fraction of mergers leading to a binary is, could it be as low as 1%? Mm-hmm. Thirty 30%, yeah. But if it's yeah, so I I would say based on that, this 90% stalling is probably on the pessimistic side of things. So even in the most pessimistic scenario where you've got a lot of stalling and then you've also got effects that are diminishing the spectrum at low frequencies, we're still looking at a detection within a decade. Yes. Absolutely. We have, uh, just in the last year, we've had Meerkat uh, come online, and it's a collection of small dishes that add up to a big dish. As we get to we're seeing the first results from that large dish in China now. So those actually have greater precision on their timing residuals than what we've. Once we have the square kilometer array, so you've got a kilometer of collecting area. That just beats down the. So there's a couple of factors that beats down the noise in each measurement, but in addition, it's expected that we'll end up discovering, using those new facilities, and especially SKA, hundreds to thousands of new millisecond pulsars, right? So we get a big boost on this N factor. So these new facilities, it's not like these are radical improvements in radio astronomy technology, but it's just they're bigger and better. So well, those are, I actually have to, I don't remember exactly the assumptions that went into making these curves about what they were folding in, but I don't think they were necessarily accounting for what the FAST telescope in China is going to be contributing. I think it did have some Meerkat pulsar maybe included in that, but so I can't remember the assumptions, but that does affect these numbers. So, but I think those detectors really are, their influence is going to be felt a little further out here. So this is probably more like based on what we kind of currently are doing, and even with that, we're in pretty good shape. But even, like I was saying, with pulsar timing, you have to be patient. Each of the, you can do the math. A nanohertz, in terms of a period, these are many, many year periods, right? So this is only a few periods of a gravitational wave before we make a detection. There's another way of looking at it. So, yes.
One related question is, in their paper, at that time, did they know of this ephemeris problem?
Yes.
Oh, okay.
But that doesn't really cost us very much in terms of sensitivity. It's a pretty minor effect. And it's going to get better because there's a mission that's heading out to Jupiter right now, a NASA mission, and it's going to be able to constrain the sort of like various directions in this parameter space that are not well constrained. And this particular mission is going to help fix the problem that we're having. So we'll actually have to spend less of our precious pulsar timing data on solving for the solar system and can use more like planetary. So I think that's all going to get better. Okay, moving on. Individual supermassive black hole binaries. So here's the timing fluctuations in the time of arrival caused by an individual black hole binary, and if you integrate the usual expression for the early in-spiral gravitational wave signals. So this is essentially just a circular binary integrated once. This is then the expression you get for the plus and cross polarizations. Here, this is the angular frequency, so just the derivative of the phase, orbital phase. So we can look for individual black hole binaries, and something I didn't mention, I should have said earlier, is that there's two terms here. There is the what we call the Earth term, so it's the gravitational wave signal as seen at the Earth at time t, and then with a time delay that depends on the distance to the pulsar and then this angle between us and the pulsar. This is what's known as the pulsar term. So that's the gravitational wave encountering the pulsar, but at this retarded time, and there's the gravitational wave reaching the Earth. Now, in the case of stochastic backgrounds, the pulsar term is uncorrelated between different pulsars because they're all at different distances, so they're sampling the stochastic background at different times, and that cross correlation is 0. Whereas for a individual supermassive black hole binary, since we have a model for how the waveform looks at one time and how it looks at another time, we can actually phase connect these components. So we can coherently search for the pulsar term as well as the Earth term, which you can't do with the stochastic, because now that requires, for that to work, you need to know the distance to the pulsar, and you actually need to know it pretty well. And better than what we actually do know it. But just to give you some numbers, the chirp time scale, so this is a characteristic time scale on which the gravitational wave frequency is changing, so omega divided by omega dot, it's given by this expression, just leading post-Newtonian order. And you plug in some numbers representative for pulsar timing arrays, and that chirp time scale is of order 10 to the 5 years. Now, our observations in pulsar timing go for decades, so you'd think, how can I possibly measure the change in the frequency when I'm only measuring it for 10 years, and the time scale for that frequency change is more like tens of thousands of years? But this is, of course, referenced here to 10 to the minus 8, so it's stronger. This expression is quite a bit it's highly dependent on the frequency, so it can be quite a bit less than 10 to the 5 years. But the pulsars are kiloparsecs away, typically. So you end up with a baseline. The pulsar is seeing the gravitational wave signal 10,000 years ago, typically, something like that. So you don't get your baseline from observing for thousands of years. No one's that patient. But we actually see the signal from 10,000 years ago, and we see the signal today. That allows us to measure the evolution. So, for example, this is from a paper I wrote with Vincent Corbin. This was a 5 by 10 to the 8 solar mass chirp mass at a frequency of 3 by 10 to the minus 8 hertz. We had just 20 pulsars. The overall signal was SNR 14. And this shows how well we could recover the distance to the black hole, the mass, and sky location. So we can actually, not very well, but we can get some kind of constraints on what the masses are this way. So as we go forward and are able to detect individual signals, we're going to be able to start doing the kinds of things you're familiar with seeing from like LIGO type analyses, where you get the masses and distances to these systems. The cute part of this is that we actually have you also have to model the distance to the pulsars. We can actually measure the distance to the pulsars from this as well. So, but going forward, we're going to actually have good distances to pulsars from parallax. So a lot of the pulsars measured by the SKA will have quite well measured distances. Where are we currently? Again, from the 11-year data set, this is preliminary results that are actually being redone right now. These are the bounds, the upper limits on what the gravitational wave strain is at each frequency for averaged over the sky for individual signals. You can see the results we had for the 5-year data set, the 9-year data set, and then the 11-year data set. Like I said, the 11-year numbers are under revision right now. We're just rerunning the analysis because of a little bit of a problem, but it's probably going to end up looking pretty much like this. So we haven't found anything yet, but we're starting to get down to some pretty good sensitivity levels. So that's averaged over the sky as a function of frequency. Here is summed over frequencies, but showing the sensitivity as a function of sky location. The little stars are our pulsars. So these are the pulsars being used in the current NANOGrav analyses. And you see they're clustered. They're all in a big blob over here, and we've got a few up here. We don't have any over here. So the red dots, the red dot here and the red dot here, mark the position on the sky that we are most sensitive to gravitational waves and least sensitive. And you see that the difference between our most sensitive, this is a 95% strain upper limit, and the difference is at least half an order of magnitude, so a factor of 3 or 4 difference in sensitivity depending on where the source might be on the sky. So as we go forward and we fold in the data from the other, in particular the Parkes timing array, which have some pulsars out here for us, we're going to get better sky coverage, and our ability to detect things is going to improve. So we have a very uneven coverage with NANOGrav on its own. That's why it's good to work as a team across continents and get the southern hemisphere pulsars as well. Right, so this reminds me of the old LIGO talks we used to give, where we just gave endless just upper limits, like, well, next LIGO paper, yeah, we haven't seen anything. We've improved the upper limit. The rate of black hole mergers is lower than what we said last time. And that's what we're doing right now in pulsar timing. So we just keep on setting upper limits, but as you've seen with LIGO, that's going to transition to detections, and we'll eventually have individual sources, which will be cool as well. Okay, final, oh, no, I got 2 last little things. So memory bursts. So there's this weird effect in general relativity where you have this oscillation in your gravitational field, but then it doesn't go back to 0. You end up with an overall DC offset. It actually builds. They call it memory because it's even after the gravitational waves, even after this binary has merged, there's sort of a memory that it happened. It's permanently sort of reset the metric. This offset actually builds up during the final phase of the merger. So it doesn't happen. It's not a step function. It's sort of this offset starts to build. That's actually what's measurable in LIGO, is the build-up. But what happens in pulsar timing, because we integrate this once, is we end up with this is what a pulsar timing response with a burst with memory. So if it was a merger occur, it actually causes a linear displacement then so just a linear growth in the timing residual. So this is something that we search for and so far have not found any indications of. This should be fairly rare. We don't expect to see very many mergers. So it's kind of a long shot that we'll actually see this, but it's a cool effect, and it's more detectable in pulsar timing than it is with LIGO or LISA, because we don't get the sort of low frequency response. Yes. That's a calculated waveform. It always happens. It always happens. This? The blue and the red? Well, one is without including the memory effect and one is with. So it's just showing that if you, it's just showing the difference between the waveform without including the memory, and the blue is with. That's what the 2 curves are. Yes? Well, if you're doing numerical relativity, it just happens, right? Because you're just solving the equations, and you just see it. It just comes out, right? You don't have to do anything. Yeah. Yes. Right. Yes, that's right. And that's what this paper by Mark Favada has in it, is the post-Newtonian calculation of the. So it's a non-linear. There's two types of, of memory effects, and this is the non-linear Christodoulou memory. So it's something you compute in post-Newtonian theory about comes from the non-linearity of you know. Oh yeah, you see this in the numerical relativity simulations. Yes. Well, no, they can go in different directions. But what I didn't say here is this is different pulsars, and you see that depending on where the pulsar, it's either ends up being a positive or a negative, just where you're catching it in the antenna pattern. So that's actually the thing that allows us, because if all of them just sort of did this, we might think it's some problem with the clocks or whatever. But depending on where you are in the sky, you actually get a different curve. And in fact, what was interesting is we had an analysis of which we haven't published yet, I think of the 9-year data where we were getting indications of a memory effect, but it was weird because all the pulsars were kind of doing it in the same direction, and then we looked at some of the Parkes pulsars, and the prediction was that they should have a term going in the opposite direction, and they didn't. So we were able to say no, it was a problem in the data, not actually. But that's why you want the sky coverage, because then you want to get. So yes.
In GR, so if you look over the whole universe, is this memory effect averaging to zero over all images?
I guess it's a random walk, right? So it's sort of a root n thing. One kick up, one kick down. Yeah, it's a weird. We've got let Cliff have a go.
Gravitational waves emitted by the outgoing flux of energy in the gravitational waves.
Right.
Energy is mass, mass emits waves. So that outgoing burst of gravitational waves emits gravitational waves. But then after that burst of waves passes you by, there's a net change in the vector because now there's mass that's
Gone.
inside you
Right.
up to infinity, and that's what causes over time this net shift.
Yeah, I mean, like if you take the first black hole merger, something like 3 solar masses got radiated away, so the Newtonian field that's left is that of all that mass, all that energy has gone past you now, and so that black hole that's left behind is less massive than what was there before, so you've permanently reset your metric. So it's a weird.
It's not just the change in mass, because
Right.
at the distance that's completely
Yeah.
it's the fact that energy is, as you're now inside the cloud of energy, there's a potential change in significant
Right.
at
Yeah,
that
that.
generates metric too.
Yeah, that's gone past you. So again, we've just got upper limits right now on the burst with memory, and for the 11-year data set, still work in progress, but we've improved from where we were, but I still haven't found anything. All right, finally, tests of alternative theories of gravity. So if you go back to Einstein's paper on gravitational waves and you read some of the sections here, he's saying that gravitational waves propagate at the speed of light, and here he's saying the two types, now talking about the polarizations, the two types are of the same nature and differ only in their mutual orientation. The wave field acts in deforming angles in a plane which is perpendicular to the direction of propagation. So talking about the two polarization states of gravitational waves. And as we heard from Cliff earlier, or 2 days ago now, I guess. It's a day ago, I can't remember. Sorry, I want to go back. If in more general theories, you can have up to 6 polarization states. So this is a prediction that's essentially unique, well, not quite unique to general relativity, but it's one of the predictions is that we should only see these 2 polarization states. So we've got the fields propagate at the speed of light, and that there should be these 2 polarizations 45 degrees to each other. And of course, with the joint detection by LIGO and Fermi and integral and everything else, we see that indeed the speed of gravity is equal to the speed of light to very high precision, so we're good on that one. We pretty much take that one as done now. But what about the polarizations? I'm not going to talk about the LIGO results, but oh, I also had some. So typically, if this is taken from a review paper by Manuel Berthe and collaborators, you really don't want to mess around with the weak equivalence principle if you want to modify gravity, because that's so well constrained. So what you can do, you can maybe go to higher dimensions if you like that sort of thing, or add in extra fields, or you can start violating things like diffeomorphism invariant. So you can add mass to the graviton, violate Lorentz violations. The sort of nicer versions of modifications to gravity bring in extra fields, so extra scalar and vector fields. Typically then you get dipole radiation and all these other polarizations. So here you're going to get all these other polarization states set up typically. So again, repeating what we saw, here's the polarization tensor for the usual transverse, sorry, this is not transverse traceless, this is tensor transverse modes. So U and V, K is the propagation director, U and V in the plane orthogonal to the propagation. So this is a purely transverse mode since it's movement in the U and V direction, and the particular form of the tensors here mean that they're at 45 degrees. Then you've got the scalar transverse, and again that just depends on U and V because it's a transverse mode. But then you've got the scalar longitudinal, which goes in the K direction, and then you've got the vector longitudinal modes, which are this one and this one, which are rotated with respect to each other, but they involve a mixture of, say, U and K or V and K, okay? So these are the polarization tensors for each of those modes, and you can just run it through the same calculation I did earlier for the response and figure out the response to these things. This is what you get as the response in an interferometer like LIGO for the different modes, and as Cliff mentioned, the scalar transverse and the scalar longitudinal is degenerate. The response is the same in an interferometer, but in pulsar timing, they're all different. So the tensor, we've seen this before. This is what the scalar transverse looks like. This is the vector longitudinal, and this is the scalar longitudinal. This is just showing one of the polarizations of the tensor and the vector. The others is just a rotation, one by 90 degrees, one by 45 of this. Now these aren't to scale here. The color does indicate the strength of the response. If I was to show them to scale, that's them to scale. So you immediately see that pulsar timing arrays are hugely more sensitive to the scalar longitudinal modes than they are to the vector longitudinal or the tensor or scale or any of the transverse modes. So there's this enhanced response to the longitudinal modes. And this is, again, for FL equals 10. These patterns get even, the difference between them gets even greater as FL gets larger, until this sort of shrinks to little dots you can't see. Okay, so pulsar timing is a very good way. There's a couple of reasons why pulsar timing is very good for trying to constrain alternative polarizations. One is you've got all these different projections of the polarization, because you've got pulsars in all different directions of the sky, so you're projecting the polarization pattern many different ways. And also there's this enhanced response in particular to the longitudinal modes, which doesn't happen at all for interferometers. Now you can go through and do the same kind of calculation. The Hellings-Downs curve, if it's a stochastic background, you get different correlation curves for each of the different polarization states. And here, the behavior at small angular separations actually scales as the logarithm here for the vector case, the logarithm of the frequency times the distance, and in the scale longitudinal it goes linearly, so there's a very enhanced response. So we set out to see how well this could be constrained using pulsar timing, and one of the weird things that happens is kind of a paradox in a way until you think about it, and that is you can set very strong limits on these longitudinal modes. So these are the kind of limits we can set with the 9-year NANOGrav data compared to what we can set for the transverse modes, so they're considerably better constrained because there's a much bigger response to those modes. On the other hand, if you do the signal to noise as a function of time, you see that the vector and scale longitudinal modes, their signal to noise grows much more slowly and starts at smaller values. This is assuming zero noise with an IPTA setup, in which case we'd have already detected the tensor modes by now. And that might seem counterintuitive, but what's actually happening here, it's the self-noise that actually is preventing you from detecting it. So it's the because it's the autocorrelation term at zero angle is so huge that these actually the longitudinal modes actually, you can't see the correlation pattern because the scatter in it is enormous due to the pulsar term. The uncorrelated pulsar term is a huge noise source which totally swamps it. So remember, to make a detection you have to be able to measure the correlation pattern, and you just can't see the correlation pattern because it's totally blown out by this massive variance that the gravitational waves themselves cause. But to make an upper limit, you don't have to see a correlation pattern, you just attribute all of the timing noise to gravitational waves with no correlation pattern, right? You say everything that's causing a timing fluctuation, all my timing residuals are purely due to gravitational waves, and since there's such a large response to the longitudinal modes, that means we end up with much tighter bounds on the longitudinal modes. So we can constrain their amplitude very well, say they're not there, but actually to claim that we've detected them is going to take a lot longer, many decades. So it's going to be very hard to detect. Now this is for stochastic. For individual sources, it's a different story, because then we can coherently capture the pulsar term and the Earth term, and so for individual sources we can actually detect the longitudinal modes quite well with pulsar timing. That paper isn't published yet, but it's coming out. A student of mine's writing that right now. So for individual sources, we'll actually be able to we can actually detect, and the sort of thing we'll be able to do is similar to what LIGO's done. Once we have a detection of an individual source, we'll be able to set, so we've detected it, we'll be able to set very strong bounds on what fraction of the signal is due to alternative polarizations, right? So if we make a detection, imagine that the true theory of gravity really is general relativity and there is none of this other nonsense, then we'll end up saying that the fraction, say, in the scale longitudinal has to be, say, 10 to the minus 3 or less of what was in the traditional transverse tensor modes, right? So we're going to get very good constraints once we start detecting individual sources. I think this is pretty much my final slide. Using a formalism we developed recently, we now have these bounds on the amplitude of the gravitational waves. This is the tensor amplitude, scalar, transverse, vector longitudinal. Oh, that should be scale. I better change the slide. That should be scalar longitudinal. And you notice that first thing you notice is that the bound on this amplitude is not as good as what we got when we did the pure general relativity analysis, but that's because we're solving for all of these simultaneously. So instead of being like 1.5 by 10 to the minus 15, which is the bound we get in the main analysis, it gets weakened to 2.2 because we have all of these terms that we're fitting for now. But you notice that the longitudinal modes, their amplitudes are much more highly constrained than that of the tensor, so by at least 2 orders of magnitude. But as Cliff was saying, that scalar longitudinal is a pretty bizarre mode to produce in a theory of gravity anyway, and if it did exist, it's highly constrained already by the data. So I think I will end there. Sorry I went long today, but please do check out Joe's Pulsar metronome demo, and there's a GitHub link here as well if you want to play with it yourself, but do come and see Joe's demonstration later today. Thank you. Any other questions? Just need a coffee. Yes. Well, no, these are very different from the kind of limits. So LIGO's also published limits on the energy density in vector and scalar modes from a stochastic search. But the thing that LIGO's been able to do that we can't currently do with pulsar timing is because there are detections in LIGO, you can compare how well the detected signals match a a traditional transverse traceless pattern versus a vector longitudinal or a scalar pattern, right? So that was the analysis that Cliff mentioned yesterday, where if you just compare, is it purely vector, purely scalar, purely tensor, tensor's favored. Of course, there's no decent model of gravity that gives you just purely scalar or purely vector. We can do a better job with that. So with LIGO, because there's detections, we can already start constraining the relative fraction, which we haven't done yet because the analysis isn't set up, but we could in principle set bounds on the relative fraction of the signal that's in vector and scalar and tensor, right? And hopefully we'll get that result out. And it really helps when you have an electromagnetic counterpart, because then you know where it is on the sky, and so you know where it should live within each antenna pattern. So the constraints you can place with a binary neutron star merger are a lot better than the constraints you can place with a black hole. And you know, if you've detected a binary neutron star with an electromagnetic counterpart, you can make this kind of bounds, and there's a paper coming out on that. It's not out. I thought it should be out by now. It's been in internal review for like the last 3 or 4 weeks, right? Anyway, so there's a paper that's soon to appear that will say more about that from LIGO's standpoint. Yeah, Joe.
I'd just like to make one comment to the students, because in the second talk that I gave, I also derived an expression for the timing residual response, allowing for both long wavelengths or short wavelengths, sort of the general calculation. But if you remember the calculation that I did, I ignored the pulsar term, and when I drew response functions, they had nice solid shapes, whereas Niels had those lobes because he precisely keeps the pulsar term. So
Right.
just to draw the connection between what I did and what Niels did.
Yes. No. We're using dispersion measure has been used to give like a crude estimate for the distance to some of the other pulsars. So I actually don't know what fraction of our pulsars we have parallax measurements on, but it's not, you know, currently it's not a large fraction of them, I don't think, and the numbers aren't very good, but that is something that's going to improve significantly going forward. So we'll have much better distances to a lot of the pulsars in the SKA era, and there's some papers by Whaley Penn and his collaborators that suggest a different way of measuring the pulsar distances using some of the scattering effects that happen, especially at low frequencies. And so he's actually claiming we can get pulsar distances to fractions of a parsec using that method. So we'll have to see if it actually works. That's right, you actually have to model the scattering screen to do this, but there's quite a few efforts towards doing that right now that seem to be able to reproduce these fluctuations in the dispersion measure and actually, you know, some of this substructure in the interstellar medium. So it's It seems a little magical, but if they really can do this, it'll be pretty amazing to get pulsar distances to sort of sub-parsec levels, and then we can use them in these analyses much more effectively. So hopefully that will happen. I don't know the details of the. There was a talk at the most recent International Pulsar Timing Array meeting a few weeks ago in Albuquerque, and those are all posted. I'll see if I can dig up the appropriate talk and get it for you. Yeah. All right, coffee time.